Okay, so today we're gonna finish up our chapter on thermodynamics. Okay, some things I'm gonna work an example out of the book because it's really hard to make up an example that works. Okay, with one of the things we're gonna talk about. So the first thing we're gonna talk about is Hess's law. Okay. Hess's law is a method which was discovered in 1840 by a man named Hess, which allows us to take various thermochemical reactions, various enthalpy reactions, and rewrite them and come up with a new thermodynamic enthalpy reaction for a chemical reaction that occurs. Okay? So what we're doing, we're taking multiple reactions and pulling parts out of multiple reactions, and in doing that, we're canceling out the enthalpies associated with those reactions. So the easiest way to do this is to look at problem 62 in the book. So in your book, this would be problem 662. Okay, and I just picked it because it was the easiest one to write. So we've got these equations. Delta H has a value for that. Delta H has a value for that reaction. Okay, so we've got those three reactions, and we want to calculate, so we want to find delta H for this reaction. Okay, so this is our reaction. This is what we're looking for, okay? So with Hess's law, we want to rearrange those so that we can come up with that bottom equation and cancel out everything else that's not included in that bottom equation. When we do that, we can add the delta H's together. Now, what is delta H? That is enthalpy of the reaction, right? That's how much heat is given off from the reaction. Now, what does the negative sign mean?
It is absorbing heat.
What does a positive sign mean?
It's putting off heat.
Well, I want it in words. Maybe better yet. What's the negative sign mean? Exothermic or endothermic?
Endothermic.
And a positive sign means
Exothermic.
Exothermic. Okay? So we want to arrange this. I'm going to slide this up, okay? Just a little bit. And let's look at this. We want 2 graphite. Do we have a reaction that's got that has graphite in it up here?
The first one.
The first one, but how many does it have? 1, but we wanna have 2. So we take the first reaction, okay? And we multiply everything in it by 2, okay? Maybe if I do this like this and we can see it a little bit easier. I multiplied everything in this reaction by 2. Okay, does that work? A little bit easier to see? Now, so we would have a 2 here, right? We would have a 2 here, a 2 here, and a 2 there. Okay? So that's our first step, and that gives us our 2 graphite, right? Now, what else do we need? We need 3 H2s. Do we have a reaction that has 3 H2s? Do we have a reaction that has H2?
Yes.
Okay, what side of the arrow is it on? Is it on the reactant side or the product side? Reactant side. So it's on the right side here, right? It's on the side that we need, okay? So for it, we would need to multiply everything times 3 because we've got to do, what we do to one, we have to do to everything, right? Agree? So now we would have 3 H2s. What's a half times 3? 3 halves or 1.5, right? And then we would have 3 here. Okay? So you see what we've done so far. Is there anything between those top 2 that we can cancel out? No. There's nothing that cancels out. Okay? So now we need C2H6 on the product side. We need C2H6 on the product side. Do we have any reactions here that we have C2H6 in?
Yeah, the third one.
The third one. But to do that, what do we need to do? We need to reverse that reaction, right? Okay. Here, I forgot to say we multiply this one times 3, right? Okay, if we reverse that, and then what do? We multiply it by a half.
1/2, yeah.
Okay? So we would reverse, and then we would multiply by a half so that we get this reaction. 3 H2O liquids plus 2 CO2 gas gives us C2H6 gas plus 3.5 O2 gas. That don't look very good. With a delta H equal to a positive 3119.06 divided by 2. Right? Since we reverse it, we change the sign from a negative to a positive, and we half it, we just divide it by 2. This one would be equal to 3 times a negative 285.8, and this one would be equal to a 2 times a negative 393.5, okay? So now, let's see what we can cancel out. Can we cancel out anything? So if we add this one, and this one, what can we cancel out?
2 CO2.
Okay, I've got a 3H2O, so I'm gonna cancel that out with that one, right? How about 2 CO2s?
Yeah.
I'm gonna cancel this out with this one, okay? I've got a C2H6 that I wanna bring down, right? What about 3.5 O2s? Is there anything on this side that we can cancel out with 3.5 O2s? I've got 1.5 and 2. 1.5 and 2 makes 3.5, right? So that cancels. So what's left on this side? 2 graphites, right? And 3 H2s. You see what I'm doing? Is there anything else? No, we're ignoring this whole third line here because we rewrote it. So I have 2 carbons as graphite plus 3 hydrogen gases produces C2H6 gas. Is that the equation that I want to make? Yes, it is. So delta H, according to Hess's law, rearranging our equations for what we know is equal to 2 times a negative 393.5 plus 3 times a negative 285.8 plus 3119.06 divided by 2. So that's delta H. Somebody add that up for me, if you don't mind.
I got negative 84.87.
Well, I haven't done it, but somebody else get that? Okay. What kind of reaction is it? Okay, so that's probably the simplest problem you're gonna work is one of these Hess's law, and all you're doing is just rearranging your equations. So it takes a little bit of practice to do it, but you don't have to figure out which equation you're gonna plug into. You just rearrange your equations. Okay, so if you're looking for problems similar to this in the book, it would be problems 61 through 64, 74, 84, and 101. Okay, 61 through 64, 74, 84, and 101 will be Hess's law. Now, question, are you gonna have a Hess's law problem on test? Yes, you're gonna have a Hess's law problem on test. Now, how are you gonna have to put the answer in? Well, the only logical way that you have to do it would be show how you rearranged your equations. You know what I'm saying? You'd have group A, I have this set of equations. This is how I rearranged them. Group answer B, would I have this set of equations? Did I rearrange them this way? Okay, so you're gonna have to kind of go along with the process there, okay? Any questions on that one? Are we good on that?
I think so.
Can I go to the next, or I'm still writing? Okay. Second law of thermodynamics. What is the second law of thermodynamics? That a system moves in direction of what?
Energy?
What? Not in the direction of energy. First law of thermodynamics was what? Total amount of energy in the universe is constant, right? Second law of thermodynamics deals with disorder.
So it tends to move towards greater disorder.
Greater disorder. So for a spontaneous change, your system moves far greater disorder. For a non-spontaneous change, it moves towards more order. Okay? Does anybody remember what the third law of thermodynamics is? that the order for a perfect crystalline substance at absolute zero is zero or infinity, right? You have perfect order. Now, it's got to be a pure crystalline solid, so you have pure crystalline structure. All Brownian motion, Newtonian motion ceases to exist at 0 degrees Celsius. That's the definition for the Kelvin temperature scale. Okay, so when you have that, you have a perfect crystalline solid with perfect order. Okay, so looking at the directions here for spontaneity. Okay, so if we've got a spontaneous reaction, and we have a non-spontaneous reaction, there's a difference in the heats. There's a difference in the enthalpy for these two, okay? Because remember, enthalpy is what? Independent of the path. It only is dependent on what? The beginning and the end, okay? So if I have a spontaneous reaction, the products are thermodynamically more stable than the reactants. If I have a non-spontaneous, what would you think?
The opposite.
The reactants are thermodynamically more stable. Now, that doesn't mean that the enthalpy is going to have a positive or negative number. That just means the difference in enthalpy is going to show whether it's spontaneous or non-spontaneous. Okay, the difference in enthalpy, not the actual enthalpy value. Okay? The standard enthalpy change for a reaction is equal to the change in enthalpy of your system plus the change in enthalpy of your, I guess you'd say your reactant. Okay? Because what's going to happen? Your reactants are going to change. Well, what is this reactant renamed as? Everything that surrounds your system. So your change in enthalpy of your reaction is equal to the change in enthalpy of your system plus the change in enthalpy of your surroundings. So think about it at home, okay? I like to use the sock drawer, okay? How do you describe your sock drawer? And we're just going to call it a sock drawer, not a other drawer. How do you describe your sock drawer? Okay, how do you put your socks in your drawer? Okay, you roll them up, fold them, put them in, but do you just throw them in there? Or is your sock drawer perfectly ordered? Like your blue ones are here, your brown ones are here, your black ones are here, your white ones are here, in perfect order, like cars parked in a car dealership parking lot. Is your sock drawer like that? Mine's not like that. But my socks are put together, so there's some order there, right? But they're not perfectly ordered. And if they were, if somebody took the time to put my socks in order, you know, like my socks with little dots versus my socks with little diamonds versus this color and that color and all that stuff, what would happen when I pull the first pair of socks out?
Order is disrupted.
I changed the order. But could I say I had zero or perfect order to begin with? No. So order, entropy, does not have an absolute value. There's no absolute starting entropy. There's no absolute ending entropy that you can define. It's only a change in entropy. It's only a change in entropy. So if we're looking at entropy, we're looking at a change in entropy. If we were looking at enthalpy, heat, we talked about this. Can we determine the total heat content of a system? No, we can only determine changes in heat content of a system. Because remember, heat was what? Pathway, or enthalpy is pathway independent. Okay, we can only look at what the change is. Entropy is going to be what? Pathway independent. We can only look at the change, not the total amount. Now we can define, in our terms, a starting point. Okay? It's kind of like when you make a drawing. Let's say you make a graph, which we don't like making graphs, but we make a graph. What do? We arbitrarily assign what? A starting point of the origin.
0.
Okay, we assign that. Okay, does that mean that our diagram is always going to have the same origin as somebody else's diagram?
Not
No.
necessarily, no.
Okay, so with entropy and with enthalpy, we're looking at changes. Now, in enthalpy, with heat, we're looking at changes in terms of kilojoules per mole. Big values on the chemistry scale. With entropy, we're looking at changes on the order of joules per mole. Okay? Thinking back to chemistry 1, what's the heat capacity for water? It's 1 calorie per gram degree Celsius. What is 1 calorie equal to? Joule-wise. 4.184 joules, right? Yes? So if that is the case, his real Dr. Pepper, his leaded Dr. Pepper, has 240 food calories, which is 240,000 energy calories. Okay? So we're talking about very small quantities. And why am I kind of spending a little time on this? Because we've got to look at these in terms of a relationship. There's a relationship that exists between enthalpy, the heat of a reaction, or the change in heat of a reaction, and entropy, the change in order of a reaction. And that relationship is called the Gibbs free energy. And it was not named after Leroy Gibbs on NCIS. Okay, it's just the Gibbs free energy. And it's a relationship that states that the Gibbs free energy is equal to delta H, the enthalpy, minus T delta S. Okay? The temperature must be in Kelvin. The temperature must be in Kelvin. Okay? Now, why is this important? Because if delta G is greater than 0, we have a spontaneous a non-spontaneous reaction. I'm sorry, non-spontaneous reaction. Which means what?
That means the
Reactants are more stable.
thermodynamically stable than the product.
Okay, that's what a non-spontaneous reaction is. Okay, based on enthalpy. Remember, our enthalpy is in terms of kilojoules, and our entropy is in terms of joules. So the only way we can get them comparable, okay, so that delta G is equal to 0, is to have a very, very small quantity for enthalpy or a very large temperature. A very large temperature. Okay, so
if we have a delta G equal to 0, what's gonna happen?
There's no reaction.
No, that's, we're at equilibrium. What is equilibrium?
When it's at a state of stability. We're gonna find out in the next chapter, the equilibrium is when the forward rate of reaction is equal to the reverse rate of reaction. So the concentration of reactants and the concentration of products is constant. Okay? Then we have delta G less than 0. We have a spontaneous reaction. So what we're seeing is that there's a relationship between enthalpy and entropy that drives the spontaneity of a reaction. So just because it's an endothermic reaction, or just because it's an exothermic reaction, that doesn't drive its spontaneity. It's an entropy and an enthalpy relationship. And that relationship is the Gibbs free energy. Okay, so think about it this way. You've got to be able to calculate enthalpies. You've got to be able to calculate entropies. Enthalpy is heat, okay? So where does the enthalpies come from? It comes from this relationship. Q is equal to MC delta T. Where does that relationship come from? It comes from the property of specific heat. Specific heat is equal to the heat over the mass times the change in temperature. So we relate everything back to this relationship within thermodynamics, okay? Because if we have heat flowing, that means we can have a relationship where heat loss is equal to heat gain. So if something loses heat, something else has to gain heat, because remember, all of this ties back so that it obeys the first, second, and third laws of thermodynamics. Can't just obey one and skip the other two. Can't just pick out two and skip one. They all have to be obeyed. They all have to be obeyed. Okay? You know, if you're driving down the highway and you've got a busted tail light and your tag's expired, but you're going 54 miles an hour in a 55 mile an hour zone, does that mean they're not going to pull you over and ask some questions and get the little pad out and write anything? No. They're going to get you for the busted tail light and the tag. And probably the insurance too. Okay? So, same thing applies when we're looking at a thermodynamic equation. It applies to enthalpy and entropy. And the enthalpy comes back to the specific heat equation, or heat capacity equation. Why? Because all substances have that property. Remember, specific heat of water is 4.184 joules per gram degree Celsius. You add a little bit of salt to it, what does it do? It goes up. Okay? You have a piece of metal. How does the heat capacity of that metal, specific heat of that metal, compare to that of water? It's lower because it's a conductor. I have a piece of plastic, hence your water bottle, hence those things back here, whatever you want to call those things. What are they made out of? Yours has got metal on the inside, right? Mm-hmm. But it's surrounded by what? Is yours plastic on them?
Plastic, yeah.
Yeah. Why?
It's an insulator.
It's an insulator. If it was just a piece of metal, what would it do?
Conduct all the.
It conducts your heat in or your heat out, depending on what you had in there. Okay, so all this is interrelated to one another. Okay, and what you'd find if you take it in more advanced chemistry class is all of that is related to the structure of the crystals that make up that compound, or the lattice structure of the molecules. When we think of crystals only at low temperature, but everything has a crystal structure. That plastic bottle has a crystalline structure. It's not crystals like hard crystals, it's the interconnection of all the carbons, hydrogens, oxygens, and whatever else is in that plastic that he's drinking, and has all those microplastics in it that are going to his brain, you know, so that he can build up that spoon of microplastics that he's got in his brain. Y'all heard that, right? Have y'all heard that?
The specifically being in your brain part, that's been debunked, but there is a lot of plastic in your body.
Yeah, a spoon's worth.
They
I have a
they-
spoon in my truck, and I look at that some days, that there's actually a spoon's worth of plastic in my body.
I read that people tried to do like an experiment about like the effects of microplastics in the body, and they could not find a control group with
There's no
with a
microplastics.
low enough amount of microplastics in the body.
Yeah.
We're all just full of plastics.
Even the people that are isolated on desert islands have microplastics. It's a bad deal. Okay, that's it for the chapter. There's some homework problems you want to work.